Good morning. So we managed to finish with calculation last time. No? I will do it in such a way that we now look briefly at these last slides of this slide set, so that we get it finished. And then for a moment, we will revisit that calculation file. I still figured out that I would like to show you something. And then we go to a next thing, which is the Crachten approach, which is this numerical partial derivative calculation approaches. Okay, but now these two last slides are about advantages and drawbacks of this ISO-GAM modeling approach. And I can say that both are quite significant. Yeah? There are significant advantages, significant drawbacks. So first of all, what is very good, especially from the point of view of science, scientific research, is that it is an investigative approach, meaning you really try to find out where uncertainty comes from. You know? And if you do it correctly, then you get the information of your uncertainty sources, and I've stressed this several times that this is at least as important as being able to estimate the uncertainty, possibly more important to know where uncertainty comes from so that you can minimize your uncertainty sources. And the tool for that you get is something called uncertainty budget. Uncertainty budget essentially is this collection of uncertainty indices. How many percent from this source, how many percent from that source, and so on. And this gives you very clear guidance where you should invest your effort and where you should, what should you pay attention to. And also at the end of this course, or as the last topic of this course, we will visit the concept of traceability. We will then see that when you establish traceability, measurement uncertainty is one of the key components which has to be there. And if uncertainty is evaluated with this ISO-GAM approach, it fits very well with the traceability. Traceability can, of course, be established also if uncertainty is estimated some other way, yeah? But this is like especially. So, all good news, yeah? Sadly, drawbacks are also quite significant, yeah? And the main thing here is that this method gives good results only when all uncertainty sources, first of all, have been found. We have to find what it is and adequately quantify. Second thing is also very difficult in chemistry in many cases. We looked at those modifications of the model. Yeah, we put in this factor and that factor, but all those factors also need numerical values and their uncertainties need numerical values. And if you think back to the example that we had, in fact, one of the biggest uncertainty sources that we had was this possible systematic effect of the endpoint, and that we just estimate. Oh, yeah, we think it's more or less that. Not so good, yeah? So obviously, this is a drawback because this is not any kind of exception. For example, if you think about things that partial analytic composition, sample carryover, contamination in trace analysis, these are terribly difficult things to estimate how much uncertainty comes from any of those things. And now the worst of all of this is that if you miss some of those or inadequately quantify, then usually you end up with underestimate. And those of you who were in the winter school You remember I showed at the end of this winter school, when summarizing the salt oxygen comparison, I showed some graph from a previous intercomparison where people had so small uncertainty ranges. One result was here, the other one was here. They were completely at odds or completely discrepant from each other, which obviously means they have grossly underestimated. And as you perhaps understood from winter school and also from what I've shown here, dissolved oxygen, if we take this as an example, is not an easy thing to measure. There are many uncertainty sources, and it's not so easy for laboratory people to really know all of them and then also to quantify. And now chemistry is especially problematic in this sense. In physics, ISO-GAM tends to work with less problems because in physics the uncertainty sources are sort of usually more easy to model and quantify and so on. But in chemistry, they are often really difficult, such as all those sample preparation related things, contamination, incomplete extraction. You can do that. And we will also see later on in this course how to do, but not really. So that even if very educated people do this ISO-GAM, they also oftentimes end up with underestimated uncertainty. And even has been this term coined, dark uncertainty. You probably know what dark matter is in cosmology. So dark uncertainty in uncertainty evaluation is similar thing. There is some uncertainty. It's evident from mismatch between lab results from different labs or results from lab and reference values of reference materials. But when you put together all your uncertainty sources and then quantify everything, you get small uncertainty, but the reference value is somewhere. So obviously you are missing something, but what it really is, not so easy. And again, then if you really very, very carefully investigate, then you end up with something like this, what IRIA has done with salt oxygen, so that you really have numerous uncertainty sources which you identify. You have made separate experiments, etc. But this thing is part of IRIA's doctoral thesis. It's not the master's thesis level of actually a doctoral thesis level of thing. And we cannot really expect routine analysis labs to do investigations at that level. And just to confirm what I just said with this slide, in order to really at least try to avoid this dark uncertainty thing, oftentimes you need to do extensive additional experiments. And again, those of you who were in winter school, you remember Irja had numerous slides where she explained how she determined iodine volatilization, oxygen coming in from reagents, and all those. And this dark uncertainty thing actually has been published by these. Yeah. And at least this person, Stephen Ellison, is possibly one of the most educated persons on this planet in measurement uncertainty in chemistry. And even he is, he's one of the authors, even he is saying that there is such a thing as dark uncertainty. So if even he is saying that, it must be really pretty. Okay. Yeah. So very good things and not so good things, come together. We will see. One of the next things we will do is to look at some kind of big picture of uncertainty evaluation approaches. we will see then one alternative approach, which is, it has numerous names, but I often call it Nordtest approach, or it also is called within lab validation approach, also top down and so on, numerous names. That approach is interesting and beneficial because you do not need to identify uncertainty. Of course, later on, you don't get as much information either. Yeah? You don't get for every you don't get such comprehensive, so you don't get anything like this from a Nordtest uncertainty evaluation. But that approach has significantly lower probability of underestimation. Okay. Any questions here? We'll then take this calculation file now again. We will do some playing with it. We'll also run this. Will later on need to be. Yeah. So what we did not do last time, but what I often do, and I simply wanted to demonstrate you, this uncertainty calculation file together with this budget enables you to play with the conditions of your measurement and see what happens if certain uncertainties go way on, bigger or smaller or whatever. So let's see what happens, for example, if now we can look at this combined standard uncertainty, for example. Suppose we completely neglect all temperature effects. Suppose we just let me rephrase. Suppose we install the best air conditioning in the world, so that the temperatures are so close, all temperatures are so close to 20 degrees centigrade that the temperature uncertainty is 0. Yeah? Let's see how much we gain. Well, yeah. Now all fits into the screen. Yeah. So if we put here 0, so let's remember it's 13.39. Yeah. Now perhaps we even let us make a copy. Well, yeah. So this is now a copy. We will same number of decimals. So it's very easy to compare. Yeah. And now we put temperature 0 and this temperature also. And if you now look 13.39, 13.37, something insignificant. And that was plus minus 5 degrees centigrade that week, which already is generous. Okay, let's put it plus minus 10 degrees. Let's see if that is, or put plus minus 15. So the temperature is between plus 5 and plus 35 in your laboratory. So this is our temperature interval. And we put here also 4. And now you see, here you now can see, so it's not 13.4, now it's 13.5, but this is less than 1% change. And if you look here, you don't see any changes. Meaning, in this measurement, under these conditions, temperature is not a problem at all. Okay. Now, let's assume it was not water, but some organic solvent. Organic solvents tend to have maybe 7 or 8 times bigger thermal expansion coefficients than water. Okay. So we have now 0.00021. If we multiply this by, let's say, 8, we get 0.0060. Yeah, let's put it 0.006. See how, suppose we do our solutions in ethanol, for example. Yeah, how that. You see, again, not catastrophic, but if you do non-aqueous work and if you really need very high accuracy, you should pay more attention to thermostatic than in the case of water. Of course, we now have these other big uncertainty sources still, so that they eclipse. Yeah? But let's now assume that what we do, we now, let me take back both of these things. Yeah, okay, now we are again back at that situation where we left off. And now let's assume we installed a titrator, potentiometric titrator. We can then evaluate that this effect pretty much goes away. Or we can perhaps put here something like 0.002 or something like that, but it essentially goes away. And repeatability with a titrator certainly will be very much better. Yeah. Now it's difficult to say how much better, but let's say instead of 0.13, I think 0.06 or something would certainly be realistic. Probably better than that, but let's put 0.06. Okay. If we look now, where is now the main possibility of making your measurement more accurate? Is it really, if you look here, should we do now? It's very clear here from this. You see, this is what I wanted to demonstrate. See how convenient it is. Okay, we make these changes. Aha, now that's the limiting thing. Okay, maybe we now should think about that. So indeed, now it's the titrant. Okay, yeah, we took a lot of effort. Yeah, now we got much better titrant. Let's see. Suppose we could get it 3 times smaller. Yeah. Again, I'm talking in very approximate terms. Yeah. So instead of 0014, it's 0005. Yeah. Oh. Now it again is repeatability. Yeah. But if we now suppose now we go again back to this non-aqueous thing, let's see if now finally temperature starts playing a role. So what was it that I put here? I think it was 16. No, I should have. We now have to make a copy, otherwise we. Okay. Good. This, and now we put here this on the. See. Now, if you go to the non-aqueous solutions as opposed to water, the uncertainty does increase, so that now temperature might be worth thinking about. Okay, I think I stop here. You probably got the message, yes, that from this, so this file can be used as a tool, very useful thing. So if you manage to get it done reasonably for any of your measurement, maybe your future master thesis or doctoral thesis, then it's a very useful thing to see where you put your. All right, I'm not. Yeah, I think I can take back here. Any questions by any? Apparently not. And then we go to this Crachten approach. So the whole idea of the Crachten approach is that we get this thing. Well, we get this thing calculated in such a way that we don't need to calculate analytical derivatives, which you see, derivatives differently from integrals, derivatives always are possible. So you can get analytical derivatives from any formula. But sometimes I've tried that with some more difficult things, and then I got derivative formulas which did not well fit into this slide. So it was so long and so clumsy and big. So it makes a lot of sense, especially these days with computers everywhere, to calculate derivatives numerically. And there's a very, in my opinion, convenient and simple approach to that. This is called the Crachten approach. This is available also as a picture or as a slide in Moodle. Yeah. I did it in the past on the whiteboard, but then if there are many participants online, then I rather use this whiteboard picture and explain here, because otherwise I could turn on video. It's not so convenient to watch, and especially video recording will not have very good quality. Not so well understood. But let's see what we have here. Yeah. First of all, let us start. Okay, that's also. Yeah, this is good. Let us start here. So what a derivative is, first of all. Derivative is the slope of a tangent. Tangent is a line, straight line, yeah, the green line here, which just touches your function in one point only, yeah? And it does not intersect, but it just touches your line. And in this point here, the derivative of your function, so this is your function, the derivative of your function is equal to the slope of the line. So the slope and the partial derivative are the same thing. Now, why do we speak about partial derivatives? Maybe even this is something that we should start with. You see, most measurement models are many variable functions. So, like this titration we had, titrant concentration, then there's the volume of the titrant, then there's the volume of the solution that you took, and in principle we could like molar mass if we wish, and so on. And oftentimes it's many more. Partial derivatives are calculated in such a way that you pick one variable, one input variable, which is x1 in this example, and all other input variables you treat as constants. So you pop, all of them are constants, and then you use the typical derivative calculation rules, yeah, so that everything else is constant and only x1 is a variable. Now, another thing, what derivative is the limiting value. Derivative is the limiting value of this kind of thing. How much y changes with changes of x1 when delta x1 streams or approaches 0. Yeah. So this is another way to look at derivative. Now, you can numerically calculate derivatives in such a way that you still use this formula. Delta x is not 0 because you cannot really calculate this formula. If it is 0, you cannot divide by 0. But you take delta x1 as a small number, something small. So you approximate derivative. You approximate this partial derivative by this kind of thing, no? With small delta x1. Small also. So we approximate derivative with this kind of delta divided by delta, where delta x1 is what we add to our current value, like let's say our titrant concentration was 0.0994. Yeah, we add some small value, and we see how much the output quantity changes. Yeah, that's delta y, and this ratio is our derivative. Okay, before I go on, please raise your hand who thinks that understood. Who did not understand, please ask. I think this is actually like gymnasium or secondary school level talk, actually, what I'm telling, but sometimes people don't know these things so well. So I want to explain as simply as I possibly. Okay, I did not mention that, but you probably understand that this thing, we look at all this thing is our uncertainty component. Yeah, you probably remember. Yeah, partial derivative multiplied by the standard answer. Okay, and now let's see. Our uncertainty component can be approximated with this way of writing. And now we will see how do we write it down. And obviously, if y is equal to some function from all these x's, yeah, as we had it, then up. Moment I will show. Yeah, so y is equal to function of all these x's. So that we now will try to write this delta y via this function. Yeah. And it's very easy actually. Yeah. Delta y is f using all the variables having the values that they had, except that to x1 we add this delta x1. And from this thing, we subtract again the value of the function, where to x1 we did not add anything at all. So that this, again, actually pretty clear thing that delta y is, and this is not an approximation, all this thing together. And please raise your hand who thinks that understood. Internet? Okay. Yeah. Now, what remains to be done is to think, okay, we said we add some small delta x1. What shall we take as delta x1? Would in principle take any small number. And now this Krachten comes in. Yeah, that was a person, yeah, who made a proposal that, look, let us take that delta x1 is always equal to the respective standard uncertainty. So his proposal was, let's use standard uncertainty of that input quantity as this small delta. And his argument was, of course, that, okay, standard uncertainties typically are fairly small compared to the quantity values. Now, if you look at what happens now, is the following. We put this x1 here will become the standard uncertainty. This x1 here also will become standard uncertainty. And the beauty of the thing now is that this denominator and this value here will cancel. No? This and this will cancel out. Was that understandable? That's the beauty of the approach. Yeah, this is why it's very convenient to take the standard uncertainty. And now we are simply left with whatever is here in the numerator. And essentially, we arrive at this equation here. Uncertainty component this uncertainty component can be approximated like this, that we calculate our output quantity 2 times. One time we add to this specific input quantity x1, we add its uncertainty. The other time we don't add, and then we subtract. And that's it. Yeah. Please raise your hand who thinks that understood. Sure. Okay. And now we will look how this thing works in practice. Oh. Okay, let me quickly share the screen here. If you go to Moodle, then you find example Krachten initial and example Krachten solved. These are now identical again. And again, I will be solving here so that this Krachten solved will be changing as I'm going. So take either of these and we will try to do that calculation. Now what I'll do, I'll open it. Anything unclear? Problems? Okay. And now when you open it, you should see almost exactly. Oh. Did you get this? No? Okay. Yeah. Good. So you may notice that it is the same example, same apple juice thing. And I've already, in order to make it faster, I've put all the data in already. So we are not going to calculate one by one all those things and so on. So the standard uncertainties are already here. What we do need to do is to calculate the value. And then all these yellow cells here we need to fill. And we also need to fill some of the green cells, and also we need to fill this. Perhaps we then start with this one because we need it for the calculation. So we again go by this formula. Let me calculate, and then I will give you one small explanation also. It's so simple to calculate, so I think I don't probably need to give it much explanation right now. And you should, of course, get the same value that we had in our previous example. So there shouldn't be any surprise. Now, if you look very closely, you see that VT-rep has been broken, or VT, sorry, has been broken down into two pieces. And this is largely for us to be able later on to calculate also those indices and things. But this is also to show you that in the case of Krachten approach, some things have to, or if you want to account for all the uncertainty sources separately, which might be a good thing to do, you need to sort of modify the model. So instead of just being here VT with all its different uncertainty sources, you now have, or we now will break it down into two pieces. One is the repeatability part, and the other is everything else. And whenever you do this kind of thing, then one of these will have to carry also the value which currently sits here. So this 11.8 something is the value. And the other one is 0. The other one is set to 0 because it must not interfere with the output quantity value. Yeah? But uncertainty of the other one is not 0. Its uncertainty is due to all those different uncertainties. So that in principle, you can do the Crachten calculation in such a way that all those temperature uncertainty, calibration, etc., everything has its own line, has its own contribution. Then you would have here sum of 4 different volume components, of which one would carry the value, all others will have 0, 0, 0, but all have uncertainty. This is the logic, modeling logic. All right, now what we will do now? Now we have to fill this table here. And here, I will explain you one thing, but yeah. So we first will put here in all these verticals, we will put the respective values that you see. And now we write here like this, equal to $C9. I'm putting dollar in front of C, but not putting dollar in front of 9. Why? Because when I'm now copying this, I will be copying this cell everywhere here. I want the C to stay constant. I want all the values to come from this vertical, yeah, from this column. But I want this 9 to change all the time, so that the next row will take the sample, etc. No? So copy, but now instead of paste, I take something which is called paste special. Also, actually, you can also take it here and just take formulas. Now, you don't see. I'm showing. Yeah. Interesting. But if I put paste special. You are not seeing at all. Yeah. All right. I have to reshare. I have to reshare my screen. Because this thing understood that I only want to share this window, but those are new windows, which doesn't show. I have to stop sharing. Share everything. Yeah, okay, yeah, now let let's go here. Yeah, so now we should be also, yeah. So now I'm taking either here formulas like this, or I can take paste special and here formulas. If you simply paste, you will, you maybe noticed in diagonals, there's slightly different color, yeah, which is useful. You will then like overwrite all that, yeah. So let's take formulas and okay, go. Otherwise, also it will copy these black borders, I think, everywhere and so on. There's nothing wrong if you simply use paste, yeah. It will simply look slightly different, but I mostly. Yeah, in your case, you might have a different version. Yeah. Okay, I usually do it with shortcut keys, Alt E S. This gives also paste special, but I guess your Excel might not give that thing to you also. But do you have anywhere this paste thing like this, looking like this? But can you now get this thing? But then use this formulas here. Formulas, F. Yeah, it's like Fx is here, yeah? If you use this one, it does exactly the same thing. Yeah, I don't know where else I could get it, yeah? Okay, let me... Arrow on. Oh, yeah, yeah. Oh, looks completely different. Does the same thing. Okay. In any case, we managed to get it done. Now, oh yeah. Now what we need to do is that to each diagonal element, we need to add the respective standard uncertainty. I guess maybe Hans or somebody who is like more educated in Excel can figure out a formula which would simply be possible to copy throughout so that we would not need to do this manually. But since here it's only 4 cells that we need to modify, so it's these 4 diagonal cells, not so difficult to do, yeah. So plus, and here, oh sorry, plus, and here we put D9, D9. Oh. Here we put again plus, and we put D10, D10. Let me save for a moment. Yeah, so now I saved so that in few seconds already your in Moodle the link should work from which you can get it. Plus D11 and plus D12. This is what you should now get. And you see that all these values here are actually very similar to what you see here, but they are not the same. All are slightly different. Now I see the inconvenience way we wrote. Yeah. I made a change to this file, but I did not think about one thing. So let us do the following so that it would be easier for us to calculate. take these 3 cells here, cut them, and paste here, like this. And then do one more thing in this formula in front of molecular mass, which is C13. Put dollar in front of C. I will explain why we need to do that. Dollar in front of C. So, paste this formula into C14 like I have now and have $1 sign in front of C13. Did you get it done? And now why I asked you to do that? Because now we can copy this formula here like this. Simply copy and paste. And you don't need to enter again all those calculations, because now it can take all the data from those same places where the data initially were. So I saved in case anybody has troubles, but now you can do that and you can compare. You should get exactly these same numbers. If you get exactly the same numbers, then all is fine. Did anybody get the same numbers? Did anybody get not the same numbers? Yeah, Elvin, what did you get? Yeah, let me take like this, yeah. Take this formula, check that you have this dollar sign here before C13. Only C13, yeah. The reason is that molecular mass is only here. Molecular mass is not anywhere here, so it has to take the molecular mass from here. And the reason why I moved it from row 15 to row 14 is that then all these all these values are positioned relatively at the same places. Yeah, so that you can. So, and now I copy and I paste it. You got it now. Everybody else got it, right? Anybody in trouble? No? People on the internet, did you manage? Anybody unhappy? Everybody happy, apparently. Okay. All right, yeah. In any case, if you get lost behind, just shout. Alternatively, you can jump to Moodle. This file is already in Moodle this way. You can see how it is. Okay. And now we need to calculate these components. Does anybody remember how that was done? Difference between what and what? Yeah, exactly. From the new value, we will now subtract the initial value. Yeah, this one. And again, of course, we want to copy, meaning we do what? Yeah, dollar sign in front of C14. Exactly what we do. Yeah. All right. Boom. And here are your uncertainty components. Done. Calculation of derivatives accomplished. Yeah. Did you get the same? should again get exactly the same numbers. Yeah? Now let me ask you one thing. Have we maybe made a mistake? Can an uncertainty component be negative? Is such a thing possible, that an uncertainty component is negative? Or if it can be possible, what does it mean? Does this sign here have any meaning? We see most signs are pluses, but one is minus. Why? But if you look at this formula here, is there any way to detect from the formula whether this minus is okay or not? Exactly. Any quantity which becomes bigger and then makes output quantity bigger, of course, will have positive uncertainty component. But whatever becoming bigger makes output quantity smaller, like this one in denominator, it absolutely has to have negative value. Yeah? So there's nothing wrong with that. And also in uncertainty calculation, we always use squares. So signs go away anyhow. Okay. Now, we had to have those components squared. So let us calculate here the squared component. And here we calculate the sum of squared components. You can now use the sum skew function with these or simple sum function with these. I'm taking the simple sum function. So let me now again wait a little bit. Did you manage? Please check whether you got the same. And if anybody wants to see any formula, shout. I will show what formula. Square. Who managed to get those same values? Please raise your hand. Why did not catch? Maybe somebody did. Nikolai, how about you? Okay, all right. Okay. Good. Now, question to you. Apparently, in this cell H18, we could now calculate the combined standard uncertainty. How do we calculate it? Square root of what? Exactly. So it's as simple as that. SQRT of this sum square. You can look at the slide. Oh, perhaps I will show for a moment. Slide that. So, in the cell H17, we calculated the sum of squares of all these components. So that, H17, and in cell H18, then we simply have to calculate. We are done. So, yeah, not really difficult. Now, the next task for you, please calculate uncertainty indexes. This is now something you should be able to do. You should be able to do. I'm waiting a little bit until you do that. And then you can, of course, put all the degrees of freedom and then this Welch-Satterthwaite components, overall degrees of freedom, etc. So all those things you can then calculate already. Whoever is fluent in those things, you can already actually finish this whole thing because there's not much to do. There's not much left to do. Did anybody manage to calculate the indices? Okay. How do we calculate indices? Who can guide me? What should I do now? Exactly. Component squared divided by the sum of squares. This is also the reason why I calculated component squares separately. I could have calculated the sum of squares in one formula without needing the line 16 at all. But for the indices, it's useful, yeah? And again, we have to put, yeah, somebody said from the audience, the dollars. Yeah, so that we... And what is now interesting to check, let us do that. This combined standard uncertainty now is an approximation because all our derivatives, partial derivatives, are approximations, they are numerical derivatives. Let's check, let's check how different it is from the analytical derivative. Yeah? So 13.3922, yeah? And now we can go to this acidity thing, yeah? And we have, no, but yeah, still, this value was the initial one, yeah? 13.393. So it's the fifth significant digit that has any change. So that the uncertainty calculated with this Crachten approach with numerical derivatives, this, in this case, is far enough good for this kind of calculation, considering that the uncertainties are in any case quite approximate. Yeah, they are not really highly accurate. Let me give you still one small warning. What can happen sometimes with Crachten approach that it does not work so well is when some input quantity, which is an important input quantity, has very large relative uncertainty. Here, all the relative uncertainties of the quantities are still pretty small, yeah? But if some important input quantity has very large uncertainty, and especially if that quantity happens to be in denominator. So for example, if this V sample would have very large standard uncertainty, let's say standard uncertainty 20% of the value, then the numerical and analytical calculation of uncertainty might differ somewhat. But usually, if one component has such a big uncertainty, this usually means that that uncertainty also is quite approximate, so that the difference is usually not really an issue. Okay, let's see now. Degrees of freedom were 30, 30, 2, and 30. Oh, by the way, let us also check how different are the indices. Yeah? Let's also look at them. So 7.5, 7.55, 32.6. Ah, yes, yes, Pui. Let me see if I can. Ah, no, now it starts. Ah, yeah. Perhaps what I'll do, I will simply reload it. Ah, no, I have to close it. Saving. Now I can reload. Oh, yeah. Now it's the right thing. Yep. So 17.17, 2.21, 46.77. Yeah, and if we now here, yeah. So here there was 17.17. Now we have 17.18, and here also small change, but they're so small that they actually insignificant for any practical purpose. Okay, yeah, let's go on then. 2 and 30. And now we put here these components, index squared divided by this one. This is 1 divided by the sum of all of these. No. And this is again pretty similar to what we had. And now the K at 95% coverage probability will be TINV 0.05. And this one. Boom. 2.3, as we had last time. Squared index divided by the number of degrees of freedom, yeah, as last time. Yeah, maybe I again did too fast. So let me stop for a moment. Anybody lagging behind? Let me perhaps. Oh, so you can see now what I'm doing. Yeah, and the overall number of degrees of freedom then is 1 divided by the sum of all those components. I have here put df component, but I would put rather Welch-Satterthwaite component. And this 8.76, I think, is again very close to what we had. Yeah, also 8.76 something. Very, very similar. Doesn't work. Should I come and help? Anybody else needs help? It's interesting. This over the years, the general Excel expertise of students has improved massively. Let's say something like 10 years ago, this same type of class meant that I was constantly running around the room. Now press here, oh, yeah, take this, yeah, and so on and so forth. But now you hardly need any help at all. Yeah. Okay, yeah, but now we are essentially done. Now what we simply need to do is to make the result, yeah. This will now be standard uncertainty multiplied by 2. This will be standard uncertainty multiplied by the k. And this is, again, essentially the same, yeah? Not essentially the same, but exactly the same, yeah? If we look at integer numbers. And let me save. So this file is now on Moodle. And I don't really know what else I should much explain here. We've sort of done. Yeah, my turn. Could you take the microphone? Yeah, we've.
I have one question also from last time. In the last exercise, we also volume of the titrant in.
Yes, we did. Yeah.
Reproducibility and.
Yeah.
But like, I understand why, but it's always gonna be like that, or we just, or I want to why and that every time.
We did it only for estimating the degrees of freedom, or two things still. Estimating degrees of freedom and also getting contribution, separate contribution from repeatability and from all those B-type components.
Every time I have a situation like that when mathematic and random error are
I would rather do, unless if it is clear that the random part has many degrees of freedom, or maybe this whole quantity is so small by significance that it doesn't really matter. But otherwise, yes, I would rather recommend this. Yeah, could you take the microphone?
Task calculation is that we calculate the repeatability of the volume of titration uncertainty, and we like multiplied 2%. Why?
Multiply 2%
in the cell F32.
F32. So why here is 2, you mean, or? Okay. Why we calculate? Now I get. Yeah. So you see, this is a good one. So the overall uncertainty contribution of titrant volume is 80.62. But out of this 80.62, in turn, 57.97% is caused by repeatability. So this is like, or let me ask you a different way. How much is 50% out of 20%? Let me rephrase. How much is half of 10%? How do you get this 10? You get 20% multiplied by 0.5, yeah? Yes, yeah. And again, since we are only picturing these values as percentages, we never put any 100 anywhere, yeah? Otherwise, we should do that, okay? 80.62 multiplied by 57.7 and divided by 100. Otherwise, we get some huge number, yeah? But now we don't need to, because this is already 0.8 and this is already 0.57, yeah? Simply Excel shows us that 10%. Did I manage to? Okay. Anybody else? Any questions? Yeah, percent of percent is not very common thing to do, yeah. But obviously, 50% of 20% is 10%, and you get it by multiplying 20 by 50 and dividing by 100. Yeah, this is how it is. Yeah. Any other questions about any of these? Okay. If no more questions, then I would actually close this Krachten thing for now. Yeah. And I think we can then go to next thing, which is the Nordtest method. Or actually, it's like we will even look more than just the Nordtest. Okay. Yeah. All right. So now, where are we? We've looked at all those, let's say, measurement-related concepts, terminology, all those repeatabilities within lab reproducibilities. We also looked at uncertainty sources, and we now also looked at one fairly good, uncertainty evaluation approach, the GAM modeling approach. And now let us take a step back and look at other possibilities of evaluation of measurement uncertainty, alternative approaches as it has been termed here. And I will briefly discuss several approaches, but mostly we will concentrate on this uncertainty evaluation based on validation quality control data, which also I oftentimes call the Nordtest approach. So, if we now speak of a routine laboratory, not a research institute, then the typical situation in a routine laboratory is like this. So, people usually more or less know where uncertainty comes from. Yeah, they mostly know that. And then people typically have lots of different data. They have control charts, proficiency testing, or let's say interlaboratory comparison measurement results. They have replicate measurement results. Maybe they have measured the same sample on different days and all kinds of things. And the question then is, how can we use these data to take these sources of uncertainty into account? And quite long time ago, in 2007, Eurolab published this technical report. Although very old, is still relevant because it conceptually broke down all uncertainty evaluation approaches into like 4 main categories. Let me also say that oftentimes uncertainty is evaluated in such a way that it's not purely any of these. It has like elements from different ones. But I think pretty much all that can be used is in these categories, and it can simply be combined in. So in all cases, it starts with definition of the measurand. So the uncertainty has to correspond to what the measurand is. remember, we have here made distinction whether it is for the sample or for the whole object, yeah, meaning sampling uncertainty either is not inside or is inside, yeah. And then there are single lab and interlab approaches. The term single lab is actually slightly misleading because sometimes you also use data for single lab approaches which actually come from other labs. I'll come to that. I will explain what I mean by that. But importantly, in those single lab approaches, you use your own data for uncertainty calculation. In interlab approaches, sometimes it can happen that you don't use your own data at all. We leave the interlaboratory approaches for the later. I'm not going to discuss them right now. I only very briefly. And now, in single lab approaches, the next question is it model-based or not? And if it is model-based, then we get what we just did. Component by component evaluation, or isogam, or bottom-up, as it is also oftentimes called. Maybe I will put this bottom-up also. What bottom-up means in this context is that you look all the input quantities, yeah, all the small things, and you build up the uncertainty of the output quantity. Okay. Then, another one, which will be the topic of most of our next lecture, which is tomorrow, yeah, is the single lab validation approach, where you use within lab reproducibility and bias data, and which I often call NORTEST because NORTEST technical report 537 is possibly the best formalization of this. By formalization, I mean documentary guide, yeah, so that you open a guide and you can go step by step and do the evaluation of uncertainty. And this is also oftentimes called top-down. And also the single lab validation approach, there are different realizations. So NORTEST is not the only possibility, but since the guide is actually very good, it's very written in very simple language for simple laboratory people not having doctoral degree or anything, then this is why I quite like it actually. And now, if it's interlaboratory method, then essentially what is used in both of these is that you take standard deviation of labs from an interlaboratory comparison and use that standard deviation as your combined standard uncertainty. It's extremely crude and usable only as a first approximation. So this is why I come to this back later after we have looked at the NORTEST approach. But I would already here say I would not even teach this approach actually. I would not teach it if it would not be in the document, and I thought it sort of bizarre to teach the document but then leave half of it out. You know? And I would never recommend interlaboratory approach if you have this method already in your own lab running. Then you should not use it. It should be used only in such a case if you don't yet have it. You only think, okay, I'd like to start analyzing this. Yeah, interesting. What uncertainty could I expect, perhaps? And then you go to those data and check what is the between lab reproducibility. If you already have it running in your own lab, I only would recommend using either of these two. Okay, so now let's now go to the Nordtest approach. We have only 3 or 4 minutes, depending on the clock, but we can do some very first things. This report is also in Moodle. It's also available online, free of charge. Everybody can use it. So what this Nordtest approach does, it breaks all uncertainty components down into just 2 pieces. Everything that causes random effect, everything that causes both. And then these 2 pieces are combined like this. Well, can't be simpler, And first of those is the random effects, as I already said, and the second one is interesting. Now read what is written here very carefully. You notice there's a word possible. You will see in many of the slides the word possible bias, possible bias, possible. Why I'm stressing possible? The point is, it's not so easy in practice to find out whether your measurement result actually is systematically lower or systematically higher, meaning whether it actually is biased at all. Because on top of a bias always come the random effects, so that you can find today, lower, but tomorrow higher, and then lower. And whether there is any systematic effect at all can be very difficult to find out. Also, it can be very sensitive to small nuances, such as, okay, today it was this kind of soil, it's lower. Tomorrow it's another kind of soil. Now I get higher results. So it can depend on different nuances of the sample composition. So today it's, let's say, this type of fish. Tomorrow it's somewhat different species of fish. Today I have pork. Tomorrow I have veal, for example. So on and so forth. So oftentimes it's not clear. So that what often is done in Nordtest approach is that you determine bias. You sort of see that there seems to be bias. You are not sure, but you still assign uncertainty to possibly being biased in order not to overlook that possible uncertainty and in order not to underestimate uncertainty. And the next thing, which is the last message for today, remember we had this short term and long term, and remember we had this that, okay, whether anything is random or systematic depends on whether we look within day or in the long term. Nordtest always operates long term. So it's not repeatability that Nordtest uses, but within lab reproducibility, preferably during roughly 1 year, okay, maybe 8 months or so, but not 8 days. I think we stop here for today. This is where we continue tomorrow. If all goes well, then tomorrow we also start already calculation example of Nordtest. So that again, please bring your computer. So we now do quite a bit of calculation. But for today, unless you have questions, if not, then thank you, and the lecture is over.